Okay, we've been talking about gases, and last time I got into a little bit of stuff there after the quiz. We talked about gas stoichiometry. So, sort of good news about really any type of stoichiometry is it's really the same basic steps, and the same thing here with gas stoichiometry. You still really do follow those same four steps. We balance the equation, we convert to moles. We also want to always, when you're doing any type of stoichiometry sort of problem, determine whether or not, obviously, if it's a limiting reagent type situation. If it is, then obviously you need to do the limiting reagent calculation. If not, it's just a basic stoichiometry. We also will do our mole to mole after that, and then our moles to some other unit. Really, what sort of varies here when we're doing gas stoichiometry is, I would say probably for the most part, somewhere along the way, you are going to use the ideal gas law. And usually, I would say in a lot of cases, at the end of the calculation, you may use this to solve for something like the volume of gas that you collected. And that's a very common sort of place where you would use it. Also, you could use it early on in the calculation, like you'll do today in lab, and you could use it to solve for moles and PV over RT. So that's also a very common way. Again, instead of using like the molar mass, if you have all the information about your gas, you can use the ideal gas law and solve for moles, and then really just roll into like a normal stoichiometry problem after that. There are cases where you may use both of them together at the beginning and the end, and that does happen. But I say those are, again, the two common places where you sort of incorporate the gas law into the stoichiometry. Kind of the rest of it is pretty much the same as you go through it. We also talked at the end there about partial pressures. So remember that when we do have a mixture of different gases in a container, the total pressure of that mixture of gas is basically equal to the pressure of A plus the pressure of B and C's contribution. And these are what are referred to as partial pressures. And again, there are partial pressures because they contribute sort of to the overall pressure of the mixture. In a lab situation, the total pressure would be your barometer reading that you would take. In a textbook type problem, they usually will oftentimes give you the total pressure, atmospheric pressure, sort of given to you. Um, one of the reasons or one of the ways that we can sort of calculate the partial pressures of a gas is also, strangely enough, using the ideal gas law is essentially the most common way to kind of do that. You would solve for, again, the pressure of A, for example. You would also, in this case, solve for B, and you would do a calculation that would solve for C as well. One of the things that makes something an ideal gas we touched upon last time is the idea that even if it's in a container with other gas molecules, there's really no interaction between those gas molecules, which means in an ideal situation, which is most of the time the situation that we deal with, we could pretty much safely assume that they're kind of in there by themselves, even though they're not. And that's why that allows us to do this type of calculation here, where we could kind of calculate each of the pressures individually, just like they were in that mixture or that container by themselves, even though they are not. One of the nice things about doing this essentially is that because they are in the same container, the volume will be the same for everybody. And also the temperature will be the same for everybody. R is a constant, which means pretty much all three of these things are going to be the same in each of the calculations that you do. So really the only thing that varies is the moles of each of the gases that you have flying around in there. Once you solve for each of these guys individually to get the total pressure, you simply just add them together, and that would give you your total pressure in that particular mixture. We saw also a little formula there that you could use if you maybe don't have enough information to get into the ideal gas law. And I'm not going to focus too much on that one because, again, you probably won't use it too much in here. So next class, we'll use it. So we won't worry too much about that one. Any questions on any of that stuff we talked about last time here? So I don't think we did the example. So why don't we do an example, one of these here? We have 5 grams of helium and also 5 grams of neon. It's in a 2.5 liter container at 27 degrees Celsius. We're looking for the partial pressures of each of the gases and also what would be the total pressure of the mixture. Helium is 4.003 and neon is 2018. So I here in this situation, we got a container, got some helium flying around, it's got some neon flying around. They are both in the same container, which means they both have the same volume of 2.5 liters. We also have the temperature for both of them at 27 degrees Celsius. We are looking for the pressure of each of them. So again, a little P equals nRT action here. We have temperature, we have volume, we always have R. We are looking for the pressure. We do need the moles, which we can get by converting our grams to moles here. So that's what we also want to do. So we'll start with our 5 grams of helium. We'll use the molar mass from the periodic table, 4.003 grams per mole of helium. Going to get us here for helium, looks like 1.25 moles. We'll do the same calculation for neon. Obviously using neon's molar mass, so 2018. And for neon here, that will get us something a little less, 0.248 moles. So we now have basically the moles, the volume, the temperature. We could use the ideal gas law here again separately for each gas individually. Because of the ideal situation, we could kind of pretend like they're in there by themselves. We just want to watch units, our volumes in liters, which is good. Like most gas problems, we do need to do that conversion of temperature. So we'll add a 273.15, going to give us 300.15 Kelvin. And once again, our R is always given to us. Or I wouldn't say given to us, it's usually never given to you, but it is a number that you have available to you. So we'll start with our helium here. So P of helium will equal nRT divided by V. Putting in our moles of helium, our gas constant, and our temperature, all divided by our volume of 2.5 liters. Liters will cancel, moles will cancel, Kelvin will cancel. It's going to leave us atmospheres, which is good as that's the only unit left, and it is a pressure unit. 1.25 times 0.08206 times 300.15 divided by 2.5. Going to give us a 12.3 here, atmospheres. And this number would represent the partial pressure of helium in this mixture. Any questions on that calculation there? All right, we're going to pretty much just tee it up here one more time and do the exact same calculation. Really, the only difference going to be the moles here. We just want to use our moles of neon. So we'll go with our partial pressure of neon will equal nRT over V, making sure we use, again, our neon's moles. And again, everything else pretty much identical since it's in the same container. Same canceling out here, leaving us just atmospheres. And that will get us here 0.248 times 0.08206 times 300.15 divided by 2.5. And 2.44 atmospheres in this case. And that would be obviously our partial pressure of neon in this particular mixture. Any questions on that one? To get my total pressure, I should do with both of those numbers. I should just add them together, right? So to get the total pressure here, going to be the partial pressure of helium plus the partial pressure of neon, which in this case is 12.3 atmospheres, plus a 244 atmospheres of 14.7 atmospheres in this case would be our total pressure here. Any questions on any of those calculations? I would say that this is probably the most common partial pressure type calculation that you do, which hopefully, as you can see, is pretty much just an ideal gas law problem done a couple of times or 3 times. You've got 3 gases. Again, everything is the same for everybody except for the moles, and then you could add them together to get to your partial or your total pressure. In this case, the major contributor pressure is which gas, helium or neon? It is definitely helium at 12.3 atmospheres. The reason for that is, any ideas? Has to do with these numbers. Helium is much lighter. Yeah. So helium is much lighter, which means it's going to be moving a lot faster. It's going to have a faster than a root square mean velocity. It's going to be flying around a lot faster, causing more collisions and contributing to more pressure than the heavier, slower moving neon, which is not going to be flying around as fast and not causing as many collisions. So it's actually because of the molar mass there of helium versus neon. That's why we have a big change in terms of the pressure. It's something like it's moving about 6 times faster actually than neon if you do the calculation. So it's obviously a lot more collisions, and obviously neon would be happening. Any questions on partial pressure like this here? Let's then talk about another partial pressure situation. It's pretty much the situation you're going to the lab today. That is pretty much your experiment. Should look something like that, except your bucket's green, I think, instead of the colorless one there. You're going to take some potassium chlorate solid here. In your case, it's going to be a mixture of potassium chlorate and something else. You're going to heat it up, and it's going to go through a decomposition reaction where it makes some potassium chloride and some oxygen gas here. In this particular case, a little balancing probably would be good. There you go. And in this case, you're going to set it up here with a jar full of water to the brim. You're going to basically fill the thing with water to the start. You're going to slap a watch glass on it. You're going to flip it upside down, not spill out any of the water, hopefully, and get it upside down into here. You'll hook it up here. And as we start to heat this gently and not to decompose fast, a little back and forth action, by the way. I'm sure you'll be mentioned, don't burn the clamp that's sitting there because you will burn the clamp to the test tube. You're going to start heating. It's going to generate some oxygen gas. Oxygen gas obviously has nowhere to go. It's going to come down through here and then into your receiving thing. By the way, the other important thing for your experiment is you have another tube that should go into the sink, so you don't give yourself a bath as it's shooting water out. So make sure you have that guy into the sink on the back end of yours. As you're doing it, it will start to bubble and it will displace the water that's in your jar. And you will end up with this empty spot here. And again, much like the experiment last week, that empty spot's really not empty. That is where your gas is going to end up. And in this case, you will have your oxygen gas there. But because we are collecting this gas over water or with water, just sort of the heat of the experiment will be enough to heat up the water, and you will also get some water vapor that will essentially come along for the ride. In this experiment, just like in the last experiment where you have the same situation sort of occurring, you're not really interested in the water aspect of it. It is really just the byproduct of how you're collecting your gas. So we usually have to do sort of a partial pressure situation to correct for the vapor pressure of water. The total pressure in this situation would be the pressure of the gas you're collecting plus the vapor pressure of water, which is basically what this is known as. And that vapor pressure of water that is usually found on a table, and that was that table that was taped to the board in the front. where you go look up that value based off of the temperature typically. So this is basically because we're collecting both of these gases. We oftentimes want to kind of eliminate the water's contribution, again, because it's really just a side product here. And that would mean that the pressure of the gas we're interested in, which would be the oxygen in this case, would be your total pressure, which in the laboratory would be your barometer reading, minus the vapor pressure of water in this case. So the nice one about this partial pressure is oftentimes it's used as sort of a correction sort of calculation, but it's basically just subtraction. So we're oftentimes subtracting off water's contribution to the pressure because we're really not interested in it. That is why sometimes in labs, like I think in your labs, they oftentimes will label it as the pressure of the dry gas. And they call it the dry gas because you're basically subtracting off water's contribution to the overall pressure. Any questions on that there? So anytime that you essentially collect your gas, like we did in the last experiment and today's experiment, where you're kind of collecting it over water, you will always have this situation, and usually always has to do this sort of correction, sort of calculation, because you do end up with basically a partial pressure situation of the gas you're interested in and really the water which you're not interested in terms of its gas. Now, how do you know it is the situation in textbook problems or problems in general? There's usually some words that you oftentimes see. Usually will mention something like you collected the gas over water, or you collected it saturated with water vapor, or it may just ask you to calculate the dry pressure of the dry gas. Those are all situations where it's probably pretty much this deal, and you do need to do that to correct for it. The idea here is like in last week, you would want to continue on with just the pressure of the hydrogen gas in your calculations. And this week, you want to continue on with just the pressure of just the oxygen by itself without the water's contribution. Any questions on that there? So as I mentioned, that vapor pressure of water is typically a value you could look up in a table, usually in the chapter of the gas. There's usually a little vapor pressure of water table in that chapter. So let's take a look at a problem here together. A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824. What is the partial pressure of oxygen in atmospheres? So the key words here when we read this, as I mentioned a second ago, is this part of it. It is saturated with water vapor. So that basically means you collected your gas over water in a water situation like we were just talking about. So we are going to have the total pressure going to be equal to the pressure of the gas plus the vapor pressure of water. And in this case, that means the gas we're really looking at is oxygen. So they gave us the total pressure, which would be like your barometer reading, 753 torr equals the partial pressure of oxygen. And again, if it was not given to you in the actual problem, that would be a value that you would have to go to the table for vapor pressure and look it up and find it for 30 degrees. And we see there for 30 degrees, it is 31.824 torr. That means that the partial pressure of oxygen would be our total pressure minus our vapor pressure of water here. And that's going to give us here 753 minus 31.824. 721 torr would be the pressure of the dry oxygen gas. Obviously here, though, they did want it in atmosphere, so we do need to use our conversion factor here. That 1 atmosphere equals 760 torr. So taking our 721 torr, dividing it by the 760. Those will cancel, and that's going to get us here 0.949 atmospheres of oxygen. And once again, that would represent the pressure of oxygen in that mixture And again, in this particular experiment, that is actually the gas we're interested in. Very rarely are you ever interested really in the kind of water gas there, or vapor pressure water. Any questions on that one there? This type of calculation as well, or just in general, how we calculated the total pressure, also allows you, if you had a kind of other type of problem where you have the pressure, say, of one gas, two gases, three gases. For example, if they did give you the partial pressure of these two gases and the total pressure, you basically could find this guy's partial pressure by just subtracting off the partial pressures of the other gases. So sometimes that's another sort of partial pressure situation. Any questions on partial pressures there? All right, so let's talk a little bit about the kinetic molecular theory of gases. Some of these things we sort of touched upon as we gone through our different sort of gas laws here in this chapter. Gases consist of tiny molecules of atoms or molecules. The particles are really small compared to really the distances between them in the container at which they're flying around. And because of that, we oftentimes will, in an ideal situation, consider the volume of the gas molecules themselves to be pretty much negligible or zero. And we really do look more towards at the volume of the container which they are flying around in. And number two here is really one of the things that makes something an ideal gas is that idea that we really just kind of focus more on the distance or the volume of the container they're flying around in rather than the volume of the gas themselves. Particles are in constant random motion. And as we talked about, is really those number of collisions that basically contribute to the pressure that we associate with gases. And as we've talked about, the more collisions that we have, the higher the pressure there should be. And the less collisions that we have, the lower the pressure there should be as well. Number four here is also really the second thing here that makes something an ideal gas. And that is the idea that even though we may have multiple gas molecules together in a mixture of gas, like we just talked about in that example, or those examples there, we assume that under ideal conditions, there really is no attractive forces between them or repulsion type forces between them. And as we mentioned, that's really why we could do those partial pressure calculations as them being in there by themselves rather than having to worry about the ones that are flying around in there. So those two things really are the things that make something an ideal gas. When you go to 1A or such, you'll learn about what is sometimes referred to as real gases, unlike the fake gases we're talking about here, or sometimes they're referred to as non-ideal gases. And real gases and non-ideal gases basically occur at really large pressures and really low temperatures. Really high pressures and really low temperatures. Those things where we ignore the volume of the gas and we ignore sort of the interactions between gas molecules don't really hold true. We do have to take them into account. So if you just about some of the things we talked about, if you had a really large pressure, right? When pressure goes up, what happens to the volume? Volume goes down, which means if you have a really high pressure, you're going to have a very small volume, which means now if you take your gas molecules in that really small volume, a couple of things are really important. The volume of the gas molecule compared to the little box I drew, they're pretty important. They're about the same size almost. They're not irrelevant rather than a really large volume. You got this little gas molecule where its volume itself is not that important. So you do have to actually take into account the volume of the gas molecules themselves in that type of situation. Also, when we have really low temperatures, the gas molecules would be moving faster or slower. They would be moving slower at really low temperatures, which means now they're in perhaps this really small area. And as they're moving a lot slower, which means they're going to be in contact with each other for a lot longer period of time than they are in an ideal situation. And that's why in a sort of non-ideal situation, we have to take those things into account. And you'll see it when you take 1A, what is sometimes referred to as the van der Waals equation, which is like the ideal gas law with crazy constants and things on it. And it looks really, really scary. The good news is pretty much even under normal conditions, even under sort of a little bit higher than normal conditions, most gases will still behave pretty ideally. And that's why we oftentimes will use just the ideal gas law. The ideal gas law is actually a more universal gas law that can be used really in any situation. When you get to 1A, you talk about the van der Waals equation, what you'll see is actually there's constants that you have to use in the equation that are specific for each individual gas. So it's more of a specific type of gas law that's used for specific gases. Here, under most conditions, even at a really high, what we might consider high pressure and low temperature conditions, most gases will still behave pretty much ideally, which is why we oftentimes will still use the ideal gas law. Any questions on that there? Number 5 is the average kinetic energy of the molecules is related to the temperature. And as we've talked about a couple of times, obviously, as we increase the temperature, we would again expect our gas molecules to be flying around faster. And we would perhaps expect a lot more collisions to occur as they are flying around. And obviously, vice versa, there, as we lower the temperature, we would expect them not to be flying around as fast and a little bit less collisions basically occurring. Pressure and temperature, which was our Guy-Lussac's type situation. If we have a rigid container, which means the volume is not going to adjust, remember, as we talked about, as we will increase that temperature, we will have more collisions because the volume is fixed, and we definitely will see a rise in the pressure, and vice versa. We will see the pressure come down when we lower the temperature due to the less number of collisions. This is our Charles law relationship that we talked about down here. And that is where the volume actually helps to keep the pressure constant. And remember, it's the volume in that situation that will adjust with the temperature to allow the number of collisions to stay relatively constant and keep the pressure constant. So if the volume increases when the temperature increases, and that's because, again, our gas molecules are moving faster, volume goes larger, everybody has a lot more space to fly around in, keeps the collisions about the same, pressure stays about the same. And again, it's that volume adjustment in the Charles law situation that allows the pressure to be maintained. Obviously, when we lower the temperature, volume drops down to kind of squeeze everybody together and again maintain the proper number of collisions as we see in this sort of situation here. Any questions on any of that there? All right, that wraps up chapter